Git operates as a distributed, versioned ledger. Its core architecture permanently records every state change across a repository's timeline. This permanence creates an immediate vulnerability if a developer accidentally stages and commits a local .env file containing an active AWS secret key. The immediate reflex is to execute a git revert, attempting to erase the file before the mistake is noticed. But git revert doesn't delete history, it appends a new state on top. The compromised key remains embedded. Because Git is distributed, that compromised data duplicates to anyone who cloned or forked the repository before the revert was pushed. Once pushed, the leaked data is out of your control. Remediating the leak requires full credential rotation, triggering a P0 severity incident across the organization. Because Git history is immutable, security cannot rely on post-commit cleanup. To protect the codebase, you must architect a proactive, defense-in-depth perimeter. This perimeter is structured across a three-stage pipeline: the local workstation, the CI/CD pipeline, and the remote repository. We begin where code is created, the developer's local environment. The baseline defense is Layer 1, the .gitignore file. This instructs Git to ignore specific environment or state files, preventing them from entering the tracked history. However, this layer relies on predefined file names. It does not inspect the contents of valid source code files. If a developer hard-codes a database password directly into a legitimate main.py script, the .gitignore configuration will permit the commit. To inspect file contents, we implement Layer 2, custom pre-commit hooks. These are shell scripts residing in the local .git/hooks directory. Before a commit executes, the script runs a regex search on the Git diff to locate keywords like secret or password, blocking the commit locally if a match is found. Custom bash scripts are often brittle and difficult to distribute consistently across a large engineering team. This operational bottleneck leads to Layer 3, pre-commit frameworks, specifically using the open-source tool GitLeaks. Standardizing secret pattern detection through a .precommit.config.yaml file eliminates the need for developers to maintain their own detection scripts. These three local layers reduce accidental leaks, but they reside entirely on the client side. A developer can still manually bypass them. Once a developer executes a git push, the code moves to the server environment. Anything running locally can be ignored or overwritten. To guarantee security, enforcement must happen outside the developer's environment. We start the server-side defense with Layer 4, historical repository scanning. Deep commit history scans establish a clean baseline. Running Git leaks detect uncovers legacy secrets buried in the commit history from previous months or years. Layer 5, CI/CD integration, serves as an architectural checkpoint that remains enforced regardless of local workstation settings. You configure a GitHub Actions workflow, a .github/workflows/gitleaks.yml file, to automatically trigger a scan on every incoming push or pull request. If a string matches a known secret pattern, the CI/CD server fails the build and blocks the code from merging. Layer 5 moves security enforcement from local suggestions to mandatory server-side requirements. The code now advances to the final stage, the remote repository itself. Here we deploy Layer 6, branch protection rules. Disabling direct pushes to the main branch forces every code change to exist within an isolated pull request before it can reach production. Next is Layer 7, Role-Based Access Control, or RBAC. Mapping granular read, write, and admin permissions ensures that if a developer account is compromised, the access is contained to their specific scope. However, an isolated pull request still carries a risk. Even if CI/CD checks pass, a developer could merge their own compromised logic or have it approved by a peer without a thorough review. To counter this, Layer 8, Mandatory Reviews, restricts the merge state until at least 2 independent peers have provided explicit approval. We refine these approvals with Layer 9, Code Owners implementation. The Code Owners file maps sensitive repository paths to the GitHub usernames of senior engineers or subject matter experts. GitHub intercepts any pull request modifying those specific files and restricts merge authorization to those assigned experts. Branch protection, RBAC, mandatory reviews, and code owners establish a rigorous governance gate for every line of code. Secure code can still become compromised months after merging if new vulnerabilities are discovered in its external dependencies. It is impossible for engineers to manually cross-reference global vulnerability databases against every package version listed in their repositories. This requires Layer 10, automated remediation via Dependabot. Dependabot parses manifest files like go.mod or pom.xml, comparing declared package versions against active vulnerability databases in real time. When a flaw is detected, the bot generates and tests an auto-remediation pull request to patch the package within minutes of a zero-day disclosure. Layer 10 enables the repository to actively defend and automatically patch itself against the constantly evolving landscape of modern security threats. This complete architecture functions as a single, interlocking mechanism. In the old model, security relied on developers remembering to exclude state files or manually checking package versions. This architecture replaces human memory with cryptographic pattern matching and automated governance. Human error in software development is a mathematical constant. This pipeline catches errors the moment they occur, preventing sensitive data from reaching the immutable history. A secure Git perimeter is one where the automated, governed path is the standard path for every developer.